hard questions, where to record to. All right, so let's get started with the very basics. All right, I know that you can all see most of what I see here, so I'm just quickly going to make myself a tiny bit bigger there. Okay, and move my things up, and then we're going to get going. Hello, can I please ask you not to write on my screen? It gets very frustrating. I really don't feel like having to clear your drawings. Cool. All right, so anybody who wants to, oh, I don't know why there's this thing. I think everybody can see the thing that says 2 kinds of charge, electrostatic, Siavola. It's one of those glitches that I don't know how to get rid of. Sometimes it gives me interesting things. At least it's an appropriate one, I guess. So we're going to get started on electrostatics. I always like to view electrostatics as being different from electricity in terms of the fact that when we're dealing with electrostatics, we're dealing with stationary charge. And when we deal with electricity, we're dealing with moving charge. All right, so there we go. Okay, let's just jump back to me. There we go. So we're dealing with stationary charge. Some people say charge is at rest, but basically it's charge that cannot move. When we deal with charges that actually are moving, that's your electricity and your electric current. So here we're specifically focusing on charges that can't move. Electro, charge, the word static, stationary. All right. So one of the things that you'll often notice, because we're specifically dealing with this idea of electrostatics, is they often talk about charged spheres, and then they always love to mention the words insulating stands. Now, I view that as being my insulating stand. It's made out of wood. And the reason that we have this insulating stand is that even if this top of the ball here that's charged has got a charge sitting on it, if the charge of the outside of the ball is maybe made out of a conductor, the electrons are able to move around that conductor, and if they can get down through this insulator, they can reach the earth. You hopefully know that by now from grade 8, 9, 10, that the earth is a giant reservoir of charge. That means that it's got an excess of electrons, so it can give electrons to a charged object if that charged object is positive, but it can also take electrons from a charged object if the charged object was negative. So quite often what we'll be doing here is we'll have a charged object on a stand. Also, something that you should just be aware of, these are the words that sometimes get thrown around, and it's important that we understand why they're thrown around, is we sometimes, so insulating stand is one of the common words that gets thrown out there that doesn't really add much to a question. Sometimes we talk about a pith ball, and a pith ball can have a charge on it, and basically what it is it's a small polystyrene ball, polystyrene because it's lightweight, that has been dipped in a layer of graphite. Graphite's the same stuff you get in pencil lead, and it can conduct electricity. So what happens then is if we put charges on those pith balls, they're very lightweight and they're able to move around the surface to get as far away from each other as possible, and the insulating stands preventing it, or preventing the charge from leaking down to the earth. So right back to grade 10 work. In an atom, we have a nucleus, and inside the nucleus, we have protons and neutrons. Okay, I hope all of this is rather familiar. Surrounding the nucleus, we have orbitals, and in those orbitals, we have electrons. When objects become charged, they become charged because they have gained or lost electrons. The protons don't move because they're stuck in the nucleus at the center of the atom. And in fact, they're very, very difficult to get out. For something to gain or lose electrons, okay, that shouldn't technically be lose. The lose should be more along the lines of, let's move that there, okay? And let's collect the other bit of it. Yeah, it's going to get big first. Okay, so to gain or lose electrons, all that you need to do in order to have an atom or an object gain and lose electrons is to rub 2 things against each other. This is known as triboelectric charging. Some people say tribo. I prefer tribo. Triboelectric charging. And that's what happens if you've probably done this as a kid. If you take a ruler, you rub it under your arm vigorously against a jersey, a silk cloth, something like that, and then electrons will move from the cloth onto the ruler, if the ruler is made out of plastic, and then that's now got a charge on both the cloth, in fact, and the plastic. And you can use that charged ruler to pick things up and to do fancy things with it. So to charge an object, quite simple, friction. You're probably walking across a very thick plush carpet, even managed to do this, where you're rubbing against the floor, and then you go and touch somebody and you give them a lovely zap. Particularly anybody who's in Joburg, you'll relate to that a little bit more. Since I've moved to Cape Town, we don't give each other very many electrostatic or static charges, but there's charges, I guess, shocks, because we don't have quite the amount of dryness, which generally tends to give you a little bit more of a static buildup. If we were to be playing around inside the atoms with the protons and the neutrons, that's then dealing with nuclear reactions. The only word I can say there is atomic bomb. Big boom, lots of energy. So that is not where we're going. We're dealing with electrons being put in, taken out. That's it. Please don't ever get caught up with thinking that protons move. I know they don't really test it at a matric level. It's kind of assumed that it's almost too babyish to get there. But it is one of those questions that might pop up occasionally and you might stumble over yourself if you aren't paying attention. So let's just quickly do a little bit of recap here. If an object is positively charged, it is positively charged because it has lost electrons. Remember that the charge on an electron is that it is negative. If something is negatively charged, it is negatively charged because it has gained electrons. Okay, so from here, I'm going to erase this. This is the last time. Here we go. All right. So if something is positively charged, it's lost electrons. To give you an idea of how that works, a neutral object has an equal number of positives and negatives. If I were then to take away electrons, the object or atom overall has a positive charge. Okay, so did everybody manage to see that? Was neutral. We removed 2 electrons. And that caused us to end up with something being positive. All right. If we then continue over here, if we have something that's neutrally charged and we want to make it negatively charged, we can gain more electrons and that will now have a negative charge. Does that make sense? Okay, just quickly going to stop sharing for just a second. Double check. I know this is very easy work. Can I please ask, I don't know who it is, but somebody, I don't know if you realize it, but you're writing on everybody's screens when you highlight. So please don't write on my drawings. My space is for me to write. I promise I'll give you an opportunity at the end. You guys can scribble all over the pages. But if I have to stop teaching so that I can reprimand people, this gets ridiculous. All right, so let's make this the last time, please. All right, let's carry on. So things become positively and negatively charged as electrons move. Okay, grade, in fact, I think this is even grade 9 work. Then what we're going to be talking about is how much charge they have, what is the charge, and how does it work. Okay, so we're going to spend a little bit of time now quickly talking about charge. Charge has the symbol Q. Charge is one of the few quantities where it can be an uppercase or a lowercase q. You'll see just now I do an explanation where I actually do one where little q experiences and big Q creates. And you can use either symbol, upper or lowercase, for charge. It's one of the very few quantities where you can do that. And charge is measured in Coulomb, which has the symbol uppercase C. 1 Coulomb of charge is an exceptionally big charge. So more commonly, we don't deal with a Coulomb of charge. We instead deal with millicoulomb, microcoulomb, nanocoulomb, and picocoulomb. Milli means times 10 to the negative 3. Micro means times 10 to the negative 6. Nano means times 10 to the negative 9. And pico means times 10 to the negative 12. So we're going to be dealing here with quantities that are usually a lot smaller than 1 Coulomb of charge. I cannot emphasize to all of you just how important it is that you've memorized this. Okay, when it comes to doing matric marking, and any teacher will tell you this if they've been involved in matric marking, quite often the devil is in the detail. And there are very many students who do really, really badly because they leave out details and they kind of think to themselves, oh, it's cool, I'll know how to do that. I'll remember it. It'll be in my head right at the end. I can promise you now, doing matric marking, it's not there. It's not there unless you put it there and you've learned it. So please make sure that you commit these to memory. Just an important thing here, millicoulomb is NC, microcoulomb is mu C, nanocoulombs is NC, and picocoulombs is PC. So just be aware of the fact that quite often in a question, you'll just see something like 6 NC, and you've got to remember that means times 10 to the negative 9. Because if you're sitting there at that point trying to thumb suck which of the 4 it is only going to be 4 options, you're going to mess up. All right. Can I please suggest right now that if any of you need any of this information, or if it isn't something that's like easy for you to recall, that you just quickly take a screenshot of everything that I've got here so that you are able to remember it and to continue. Okay. All right. I'm going to count to 3, not counting loud, and then I'm going to delete it all. All right, so let's clear all drawings. Okay, so far what we've looked at is just the idea of how charge is created. It's by electrons either being lost or gained. And it's almost the opposite that happens in terms of positive and negative. And that's because the electron has a negative charge. Just remember that. Otherwise, it'll make your life a little bit tricky. Okay, then there are 2 other concepts that you'd have dealt with in grade 10. The first is called the law of conservation of charge. And basically, this says that the total charge of an isolated system remains constant. All right, so this means that if we've got a whole bunch of charged objects and we add together all of their charges and then we touch them however many times we want or however much we want, the total charge afterwards will be the same. And the reason, quite simply, is that charge cannot be created or destroyed. Electrons that were there to begin with, the electrons and protons that made those charges, are not going to disappear. They're there, they stay there, and they just get moved from one object to another. So the charge itself isn't actually going to be changing. So usually, up until matric, I think even including matric, we usually only deal with 2 objects that get touched together and then separated. It is possible for them to test you with 3 or 4 or 5 or 20. The principle is the same, but here we're going to assume that we just got 2 and we're touching them. This formula is not on your formula sheet. It's one that we expect you to know. Because we expect you to know it, usually you get a mark for substitution, but not for the formula. The equation is Q, that's charge of each object after they've been touched, is equal to Q1 plus Q2 divided by 2. Basically, we're working out the average. So if we've got one charge that is plus 5 nanocoulombs and another charge that's minus 6 nanocoulombs, that's nano, and I ask you, these 2 are brought together to touch and then separated, what is the charge on each? Now, we're going to throw in a couple of other ideas while we're doing this so that I can start building up ideas that we can relatively quickly get to where matric is. But you hopefully know that a positive and a negative charge would attract each other. I usually show that by just pointing arrows. Something else that you hopefully already know is that even though these 2 charges have got different size charges, 6 is technically bigger than the 5, the forces are exactly equal. That's using the ideas in Newton's 3rd law. Object A exerting a force on object B, equal forces. We're also going to see when we hit Coulomb's law that makes a little bit more sense in terms of why they're equal forces. When these 2 touch, electrons are going to move. And the electrons will always move from the object that has more electrons to the object that has fewer electrons. In this case, the object that is negative or more negative or less positive, any of those, is always going to be the thing that has extra electrons. So when these 2 touch, the object the electrons would move, usually would be given letters here. I'm going to go A and B. For some reason in electrostatics, sorry, please stop that. Can you delete it right now? You got to go into your own screen and push clear. Thank you. Sorry, I've lost a train of thought. It's not fair. Sound like my mother. So when these two objects touch, you need to remember that only electrons can move. So since the electrons are moving over here, they'll move from the negative to the positive. Sorry, that's what I was going to say. I've labeled these A and B. I like A and B. For some reason, they like in electrostatics to call them P and Q. Don't know. So over here, we can see the electrons will move from B across through to A. And afterwards, we can go and work out what the charge is on each of them. Interesting thing, whenever they touch, they must have identical charges on them. So usually after two charges are touched, they will both want to repel each other. They'll either want to repel each other or they'll be neutral and completely indifferent to each other. So there's no force being exerted. All right. So if I continue with this over here, once they touch, the charge is relatively easy. When it comes to them touching, you're allowed to cheat, because if I put in here 5 nanocoulombs and minus 6 nanocoulombs, there's a positive, negative in here. So I can put that if you want to. It isn't going to really change the answer. I'm going to end up with negative 0.5 nanocoulombs. If you'd chosen already to start using what you know about nano, you could have made this 5 times 10 to the negative 9 and negative 6 times 10 to the negative 9, and you could have worked from there. All right, and then you'd have just ended up over here with an answer of negative 0.5 times 10 to the negative 9 coulombs, which, if we're doing a good example of scientific notation, would become negative 5 times 10 to the negative 10 coulombs. All right, does that make sense to everybody? Okay, I'm just quickly going to stop sharing and just double check. Sorry, I'm going to ask that doesn't make sense. Yeah, I've got some thumbs up. Let's see. Okay, cool. Most of you are still with me. Good, because this is grade 10. We've still got a way to go. All right. So when we touch the two objects together, we can work out the charge that's found on each. Okay. All right. Thank you for the thumbs up. Okay, so that is our law of conservation. Yes, Ibrahim. Do you have a question? You're going to have to unmute yourself to ask it. Yes?
No, it's okay. It's okay.
Okay,
I know, it's okay.
All right, you figured it out. Okay, cool.
Yeah.
So, you see, raising hands, I can see it. It works very efficiently. So when we do the charge, it's two objects touching. Now, I just quickly want to go into a little bit more detail here as to why it is that the electrons move. When we touch two charged objects together, particularly if the outside of them is a conductor, which is often the case, we aim to have two metal balls that touch, and because they're metal, their conductors and their charges can move around them, or they're pith balls, and the outside is made out of graphite, so electrons can run around. When we touch them, the electrons will automatically move from where there are more to where there are fewer, because the electrons are repelling each other. Imagine that I took a classroom filled with kids that didn't like each other, and then I told them they could go into a bigger classroom, they'd automatically move and spread out. Okay, you'd end up with the back rows being filled first, like what quite often happens at school. Because if you want to be repelled as far away from other things, you'll take up a large amount of space. So when the electrons that are slightly more electrons than B touch A, they'll very quickly move across to the other side. And they'll actually move as far away as they possibly can from each other. And because of this, they'll be evenly distributed across both of the objects. When you then separate them, provided that the two charges are exactly the same in size, you'll end up with a half of the charge on each. In Matric, we don't overcomplicate things by making one bigger and one smaller, because if we did, we actually couldn't make this big assumption here that it's divided by 2 and that they're exactly the same. All right, if these are both negative 0.5 nanocoulombs afterwards, they've both got the same charge, which means that they would then repel each other. Okay. Is everybody good with the idea of law of conservation of charge? I'm not going to be checking now because I can't actually see all of your thumbs up, or I guess you don't have a thumbs down here, but I'm just asking, when I say, is everyone okay, that's your opportunity to interrupt me then, because it's a good time to do so. All right. Okay, let's keep going. So far we've looked at those two ideas. The next thing that we need to look at is the idea of quantization. Let's try spelling. Quantization of charge. So the quantization of charge tells us that charge is found in discrete, don't panic if your teacher didn't tell it to you this way, is found in discrete packages. Basically, all charges that we ever find will be a multiple of the charge that we find on one electron. All right? This is the first of the equations that I'm going to discuss with you that's actually one of the ones on your formula sheet. So on your formula sheet, this is what the electrostatics formula sheet that you get looks like. You'll see all of these different equations, and we're going to be dealing with the first equation now, which is that equation. And that equation, I'm specifically linking it here because I find that if I tell you exactly what to look for on your formula sheet, you're more likely when you're doing past papers to know what to look for. This equation links the total charge on an object to the charge on an electron. I'll show you where to get that from just now. Charge on an electron, and N over here is the number of electrons. So N is how many electrons we've got, Q is the charge in coulombs, and E is the charge on each electron, which is given as 1.6 times 10 to the minus 19 coulombs. And you can in fact find that, I'm just going to jump across, I've got to stop sharing here, it isn't going to allow me to keep my picture there. I think one of the places, there we go. Okay, so this is your Matric formula sheet with all of the questions. And if you jump right up to the top, just telling you this because sometimes they're not going to tell you, and if nobody's ever told you where to look, you won't know. But over here, there's the value. Charge on an electron is E, and it's that value over there. Okay, so hopefully, yeah, thank you. So hopefully that's where you'll all know to look. Please, just something that is important, it's given with a negative, but when you plug it into an equation, you are allowed to make it a positive and then just look at the fact of whether you're gaining or losing electrons to decide whether the whole thing is positive or negative. All right. Okay, so jumping back to my board. There we go. So charge is found in discrete packages, and we're going to work from here. So our equation was N is equal to Q over E. Please remove it. Sorry, I really hate to be pedantic, but it's stressful enough teaching 158 people without having to discipline. Please. Cool. All right. Yes, sorry. I've got getting messages from people. Is there a question, just quickly? Okay. All right. Sorry. Ladies and gentlemen, I offered this at my own free time, and I don't know who it is in here. This is being offered to matrics, not children. I really, really can't believe that I'm having to say this, but I really am not doing this for people who aren't appreciating it. This is taking a huge amount of my family's time. It's a commitment I made from now until September. And if I'm going to have a problem because I'm dealing with immature children, it's going to be a big issue. Okay. All right. So at this point, short of us discontinuing classes because one person keeps drawing on my screen, kindly stop it. Okay. I've got a couple of my students here who will tell you that I am enough of a brat that I will stop these lessons because people are drawing on my screens. All right, so please stop it right now. Okay. All right. I don't know quite how to get rid of it. There we go. Okay. If you wish to, you can make notes on a piece of paper. It works just as well. So if we were to look at an idea here of how charge works, if I were to tell you that an object has gained, let's make it 20 electrons. Sometimes it's small amounts, sometimes it's big amounts. So an object has gained 20 electrons, that's mentioned somewhere in the blurb, and then the question comes in and asks you to calculate the charge on the object. Okay, it's relatively straightforward. You've got to look at what you've been given and what you're looking for. You're looking for the charge. The number of electrons is 20, and the charge on each electron is 1.6 times 10 to the minus 19 coulombs. So from there, you can rearrange the equation. Now, my experience is that in the Western Cape, we are happy with people substituting straight into an equation. When I taught in Johannesburg, the teachers there used to actually freak out if you rearranged an equation, because they would, when they marked it, they'd mark according to exactly the equation that was given on the formula sheet. So if you're in the Western Cape, you're fine with rearranging the equation. The rest of the provinces, please listen to what your teacher says. It probably overrides what I'm about to do here. So I'd go and say 20 is equal to Q over 1.6 times 10 to the minus 19. I'm not going to put in the negative here because I know that it's gained 20 electrons and my brain immediately says it's negative. If you don't want to, you're welcome to put in a negative here. It'll be fine, but it's just tends to be the information that I've been given that we don't put in the sign, and then the sign comes right at the end. So if I rearrange that on my calculator, 20 times 1.6 times 10 to the minus 19, we get an answer that the charge is 3.2 times 10 to the minus 18 coulombs. So it's quite straightforward. Now, I want to quickly pause here with one of the slightly harder questions at a very simplistic level that uses the two ideas we've already done. And that's that I can ask you how many electrons are lost or gained when two objects touch. And the reason I can ask this question often is really badly answered in Matric because nobody goes back to teach you from grade 10. So when they ask a grade 10 question, everyone can do 11 work, but they've forgotten the grade 10. I'm going to quickly do this. I just want a show of hands. Who would like me to give you one that's a challenge and not tell you how to do it, but to give you an option to do it yourself first? I'm just going to quickly pause so that I can actually see. So your options are who wants a quick challenge to see if they can do it first, and who would rather that I gave you the answer and showed you how to do it. Okay. Oh, I see surprisingly few hands here. Okay. Who wants the challenge? Put your hands up quickly if you want the challenge. All right, it looks like roughly 1/10 of you. 1/10 of you want the challenge. I'm not going to give you the challenge. I'm going to jump straight in and I'm going to show you how. And then maybe what I'll do is I'll give you one straight afterwards that you can practice. All right, so 10 of you, 9 of you. Yeah, sorry guys, you're really in the minority here. I'm going to quickly show everybody how to do it because it is a bit of a challenging one. And then once we've done it, I'll give you another one and then you'll know how to do it and you'll get it right. Okay. So the idea here, and please, you're going to have to excuse me. I know sometimes when I write things down, they don't come out very clearly in terms of English. There's a reason I'm not an English teacher, but you'll understand what I mean. Okay, so I'm going to tell you the story as I write down specific words in the question. We've got two objects, P and Q, and P has a charge of -3 millicoulombs, and Q has a charge of, let's make it positive 8 millicoulombs. And these two are brought to touch each other and then separated again. My question could be calculate the number of electrons that move from P to Q. All right, sorry, I'm just quickly checking the chat. Oh, I have had a question raised. Thank you very much. The previous question that I did, let's wait a second. The previous question that I did asked what was the charge, and Alex is 100% right. I'd mentioned when I did the writing out that it was negatively charged, and I knew it. But when it came to my final answer, I never actually said it was negatively charged. Thank you, Alex. Please do interrupt me. I am, especially at nearly 8 o'clock at night, I'm perfectly good with making mistakes. All right, so it should have had a negative charge on it. If you ever ask for what the charge is, you must indicate plus or minus. We assume an absence of writing a charge is assumed positive. You're 100% right. That previous one had gained electrons, gained 20 electrons, and I wrote down that it was negative, but I never wrote it with the answer. Okay, in an exam, don't do that. The examiner's not going to be as nice as I'm being to myself right now. Okay, I'm like, yeah, no, it's cool. The examiner's not going to be, yeah, no, it's cool. It'll be, yeah, no, it's cool, sorry. Okay. The question is to calculate the number of electrons that move from P to Q. I find that this is where my students often mess up because they're really good with the two equations. They're perfectly happy with Q1 plus Q2 over 2, that equation, and they're perfectly happy with saying that the number of electrons is the charge over 1,6 times 10 to the minus 19 coulombs. Both of those they're fine with. But then they get to this one and they start doing weird things. So first thing that I'm going to do is I need to work out the charge on both P and Q after they've touched. That's going to be using that formula. So I'd say that the charge that they touched, and I'm not going to change milli across here. I can get away with it still for now. So I'm going to say negative 3 millicoulombs plus 8 millicoulombs divided by 2 is going to give me 5 millicoulombs divided by 2 is going to give me 2.5 millicoulombs. Yay, and it's positive. That means that after they've touched, both of them are going to have a charge of 2.5 millicoulombs. Okay, now the question here is how many electrons moved from P to Q? What so many people are now going to do is they're going to jump into this equation and they're going to stick a value of Q in that's this value. I didn't ask you how many extra electrons does Q have after they've touched. I want to know how many electrons moved. So what I actually have to do is I have to work out the difference in charge and then divide that by the charge on each electron. So it's very important that you always identify where the question is how many extra electrons or how much charge on that object or how much charge changed. So whenever we do anything that changes, it's a very good physics and maths thing to be able to say change in charge. Delta Q, change in charge, and change in anything is always final minus initial. So my final charge here is going to be 2.5. I'm still going to stick with millicoulombs because I can. It's only later that I'm going to know I'm going to have to change it away. My initial charge now, I can deal with either P or Q. So I can look at how much P changes by or how much Q changes by. As a rule, these will give us two answers that are exactly the same, but one is positive and one is negative. So they've got the same magnitude, but opposite signs, because one's lost that amount of charge and one's gained that amount of charge, or one's got that amount of negative charge and positive charge, depending on which way the electrons move. So I'm going to do it for P here, but I promise you'll get the same answer if you do it for Q. So this is my final charge, and it's positive, minus my initial charge is negative 3 millicoulombs, and we end up with an answer that gives us positive 5.5 millicoulombs. If you'd worked it here, so this one's positive 5.5 millicoulombs, you did the exact same activity, so this minus that, you'll end up with negative 5.5 millicoulombs. Okay, sorry, I've just quickly checked here. I have got it officially from the Chief Examiner of the Western Cape. They must never sub a negative value for Q or E. The only time they ever use the negative Q is to calculate the charge after touching. Sorry, I had to check that today because it's one of those weird things where I've been told it so many times and then I always worry that I've maybe got it wrong. But this is now official. Okay, so I was right there. So over here we've got the change in charge, and when we want to work out the number of electrons, you can, in fact, here to also say it's the change in number of electrons, is instead of saying just N is Q over, you can actually say change in N is change in Q over 1.6 times 10 to the minus 19. Please note, if you're not so hot on the change in and you don't put in the delta, nobody freaks out, okay? It's one of those things that people that are very good at the maths aspect of physics want to. All right, just wait a second. Do you have to show the formula for the change in charge? No, but I'll show you which formula you do have to. And okay, I'll repeat the thing. Sorry, got the the note here. Sorry, I did check this earlier today because I suddenly had doubts. You must never sub a negative value for Q or E. Okay, so whenever you substitute, the only time you ever do it is here when they're touching. So if I'm now going to put things in here into this equation, I will never make this value negative and I'll never make that value negative. So it's just that you should never, when you use this formula here, neither of those should ever, the Q and the E, this is technically E. When I said E, it's your E value, which is it's technically negative 1,6 times 10 to the minus 19 coulombs. But you don't put in the negative. You look at whether it's lost or gained, and then you work from there. Okay, this is what I mentioned when I was doing it. Okay, so over here, if I now do this, I would write in my formula, I just throw it somewhere on the page, that N is equal to Q over E, and then I'd put it in. A large number of students don't realize that this gets a mark. And if this isn't here, sometimes we can get very sticky about what else gets marks later as to whether we're certain that you were talking about the same thing or not. Okay, so just be very careful. Over here, this is going to be 5,5 times 10 to the negative 3 divided by negative 1,6 times 10 to the negative 19. And if I work that out, 5.5 times 10 to the negative 3 divided by, you see, now I told you I wasn't going to do it, and then I went and stuck it in. Let's lose those negatives. Divided by 1.6 times 10 to the minus 19 gives me an answer of 3,44 times 10 to the 16, and that's number of electrons, so you can write there just electrons. We know that they've moved from P to Q, so if we were talking about specifically how many electrons does P gain, then you can write gains if you want to, and if it's how many do they lose, you can write loss there if you want to. Now, just one quick thing. On my calculator, it says 3,4375 times 10 to the 16. A lot of people panic about decimal places. If you read the instructions on your physics paper, it specifically says all numerical answers must be given to a minimum of 2 decimal places. That means, very importantly here, that if you give me more than 2, that's okay. It's a bit of a waste, and it sometimes gets very frustrating when you're marking and they've written down everything on the calculator. A large number of students are very weak with scientific notation, and it's very important that when you put this into your calculator, you put brackets around this number. Otherwise, you're going to take this number divided by this, and then this 10 to the negative 19 goes to the top, and suddenly you end up with an answer that's completely ridiculous and tiny. You should know that we can never have less than an electron. You don't get fractions of electrons. This whole concept here with quantization of charge says that you can only ever get whole electrons moving. You can't get a fraction or a part of an electron moving. So if you ever end up with an answer for number of electrons and it's a fraction or it's times 10 to the negative something, it's wrong. All right. Where's the question? Okay. All right, just quickly, I've got a question from Luke. How many marks would this type of question be worth? You actually hope you get a question like this. All right, I'm guessing here, so this is just my opinion. Other examiners may not agree. I would say that there's 1 mark for that step. There isn't a formula mark there. There might be a mark for doing the subtraction or the change in charge. There is another way around to do this where instead what you do is you work out the number of electrons here. So you use this equation for this charge and this equation again for the charge afterwards, and then you subtract the 2 numbers of electrons. That gives you the same answer. So there is another mark, but it would be a subtraction mark at any point that you did this value and compared. there's definitely the formula mark, which I've already given you. There'd be a substitution mark at some point and an answer mark, 5 marks. Okay. I think when I test this, it's usually around about 5 marks. There was just one other question, sorry. Why is the answer not just 5.5 millicoulombs? All right. The reason is the question wasn't what is the charge on the two objects once they touch. If it was that question, then the answer is 5.5 millicoulombs. But here what we had to do was realize that the question was how many electrons, which means that we're looking for N. And it's not just how many electrons are there on P after they've touched, it's how many electrons move from P to Q when they do touch. All right. Okay, I'm going to quickly pause sharing here for just a second because I want to ask all of you who, and this is a brave question, I guess, for me to ask, who already knew how to answer that question? So if you are pretty confident that you'd have been able to do that already, you can quickly give me a thumbs up just so that I can see. Okay. All right, this tells me it was probably worth doing because I think less than half of you knew, kind of less than half of you knew how to do it. Okay. The good news is if you can do all of that, you're done with grade 10. Okay. It's going to take a little while sometimes for me to get into how to do this with a large group. So today's very much a trial of me testing how fast I need to teach. And also, I don't want you falling asleep. I know one of the problems sometimes when you're behind a computer screen is that you don't have to give me feedback. You don't have to stay awake. And you also might be sitting there and playing on your Xbox at the same time because you think you can multitask. So it is one of those minor problems, but I'm hoping that we can get through the easy stuff so that we can drag everybody with us, hopefully not drag, take everybody with us to the point where we move on to the fun stuff for this year. Okay, just quickly, who's found that they've learned something? Anything? Okay. All right. Okay, cool. Now this is important. I need to just have an assessment as to whether I'm teaching you things that you already know or where we're going there. All right. Okay, we've still got half an hour. I don't know if anybody wants, my husband's just done a pretend to fall asleep face. I don't know if anybody here wants to just quickly stand up, stretch their legs, and then we'll carry on with the last half an hour where we move on to the matric work. All right, so I'm going to suggest that everybody just quickly stands up, moves around a little bit, because otherwise you are going to fall asleep on me. I'll usually try and give you a break when we're doing an hour and a half. It's a long time. Today we did those start 15 minutes in with me talking to you about how to do it. So just quickly stand up, move around. Don't go too far. You don't want to leave your computer. And then we'll get started again. All right. Okay. I just had a question from somebody here saying, is the last half hour for matric work? When I say matric work, I actually mean grade 11 work. Most schools cover all of this in grade 11. So it's, yeah, it's technically grade 11 work. Sorry, MZ. You are correct. I am wrong. Okay, everybody stretched a little bit. Can we get going again? Okay, cool. I've had a couple of head shakes that tells me we're able to get going. All right, so what we're going to move on to now is Coulomb's law. Now, one of the minor problems that comes in with Coulomb's law is if you're particularly weak on the previous sections that you've done, which are vectors, which is not technically examinable as a section matric, or if you so usually vectors. If you're weak on vectors, sometimes Coulomb's law can be a problem because they start bringing questions where you've got forces this way, down. You've got to consider gravity and tensions in strings. So I'm going to start off by just focusing on really straightforward Coulomb's law things. And then we're slowly but surely going to work from there. I do not think in the time that we have today, we're going to manage to reach the section on electric fields. So the whole idea with us doing a Tuesday followed by Thursday is if there's anything that I don't manage to get to, I can move it across and we can get it covered between the two sessions. Okay. All right. Whew. Time for me to breathe in, breathe out, and let's get going. All right. So we're going to now be moving on to the idea of Coulomb's law. Coulomb's law is the law that we use to calculate how big the force is. So you remember when we were dealing with the little charges, I told you if we had two like charges, they would repel each other. I think I mentioned that. And if so two like charges, whether they're both positive or both negative, they will repel each other. And if we had opposite charges, regardless of which way around they are, they would attract each other. When you were in the lower grades, you were quite happy to just say attract and repel, and that was it. We're now looking specifically, just in case you don't know all the words, at the electrostatic force. So an electrostatic force is a force between two charged objects. So electrostatic forces are specifically between charges. And when we look at Coulomb's law, we're going to be applying it directly. Now, I'm just quickly going to do a side share to my screen because I need to jump back into here with this formula. This over here is Coulomb's law. F is equal to K Q1 Q2 over R squared. Okay, so that is on your formula sheet and you do need to be aware of it. Okay, and then jumping back to where you find the value of Q. I think I've just drawn on this permanently. Let me just quickly clear it. No, go away. Okay, so our our K value is given over here, that Coulomb's constant, there, and there. So it's 9 times 10 to the 9. Please, you can cheat here and get away with just 9 times 10 to the 9. And as with all of your constants, I find that it's actually easier for me to tell you to completely ignore your units, not the 9. The 9 is important. The 9 is important, but the Newton meters, all of the units, when it comes to a constant, tend to confuse you and make you do stupid things and make you substitute things in and square them and just ignore them. Okay, so here we're going to be using the value of 9 times 10 to the 9. Okay, so that's the Coulomb's constant that we're using. There is, just in case you're interested, there is another version of it that you can use depending on if you use different units, but not at a matric level. Okay, so let's go back to my normal whiteboard screen and we're going to work on this idea. So the equation is F is equal to K Q1 Q2 over R squared. Now, F is the force. Technically, it's the electrostatic, it's the electrostatic force between two charged objects. K is our Coulomb's constant, which is just a value that you can always use and plug in as 9 times 10 to the 9. Q1 and Q2 are two different charges that we're looking at the force between, and it's measured in coulombs, and R is the distance between the two charges. Very importantly, because this is where most people lose their marks, is the distance between the two charges measured in meters. That means that you have got to convert centimeters and millimeters to meters. I'd like to hope that I don't need to do this, but because I've been teaching for as long as I have, let's just quickly go through it. You need to know that there are 1,000 millimeters in 1 meter, and there are 100 centimeters in 1 meter. So if I tell you that there are 25 centimeters between two objects, please do me a favor. I can tell you right now it's 0.25 meters. I'm pretty certain that half of the people here could. But if you need to take up your calculator to go 25 divided by 100 to get the answer, I'd much rather that you did that than you wrote down 2.5 or 0.025, or you kind of got the right number, but give or take a factor of 10. So rather if you're in any way uncertain, check it rather than guess it. Okay, so we can look at the force between two charged objects and how big that force is by simply plugging everything that we need to in it. Okay, can I please double check here? Has everybody taken a screenshot of anything that they want from this? Because I'm about to clear the screen because I actually need a little bit more space to do a calculation. What we're going to do now is we're going to do a calculation with two charged objects before they touch the electrostatic force, and then we're going to do just a little bit of practice of what we've already done. When they touch, how big the new charge is on each, and then what the new force is if they return to their original positions. Okay, so let's get started. We have charges A and B. This one has a charge. Now here's where you've got to know some of your things because you've got to convert everything to coulombs. So let's make this 15 nanocoulombs and 8 nanocoulombs. Oh, I'm not going to make them different units. We very seldom see things where one is in nano and one is in pico or any other unit. So we've got these two. I'm going to place these a very small distance apart because the electrostatic force isn't going to be so big with these being nanocoulombs. So if I ask you what is the force between these two charged objects, I'm going to suggest anybody that's at home right now that thinks they can do it or thinks they can do it faster than me, I'm challenging you right now, please get going. I'd like you to. So F is equal to K, Q1, Q2 over R squared. I'm going to do all of my working and substitution, but I'm going to do it quietly, that all of the people that are working do so without hearing what I'm saying. Okay. Habits. I am still here. Okay, now I'm hoping very much that my calculator skills are not falling asleep. Can I quickly ask everyone just quickly to glance up? I'm going to check who got it right just now. So can you just quickly check up and tell me whether I need to redo it or whether we've got the right answer? Okay, judging from the fact nobody's yet corrected me, I think we got the right answer. What you should also note is that because these have got opposite charges, there would be an attractive force between them. You do not need to put in the mention of the fact that it is attraction, but sometimes if you're specifically asked for a force instead of a magnitude of a force, you may want to hint to a direction, and I regard an attraction as being sufficient direction if I'm not talking about either A or B. Okay, so just quickly pausing my sharing here. Can I quickly ask who managed to get that right on their own? I'd like to think a large number of you remember how to do this, and it's not completely foreign. It's something that you've done once upon a lifetime ago. Okay, fantastic. All right. So it looks like most of you have managed to do that, which is wonderful. Okay, so carrying on with where we were at, this is how we do Coulomb's law. You do need to know the definition of Coulomb's law. Okay. Just wait a second. Whoa. Too many questions. Okay, so one at a time. Why can't the force be negative though? Because in this case, we'd usually be looking, the negative would only imply a direction. Okay, you must know that with forces. Forces, the negative, if we ever got it, implies a direction that's the opposite of what we've called positive. Here, if you substituted your values in, you would get a negative. And all that negative tells us is one charge is positive and one charge is negative, which means that they repel. They attract because they're opposite, one way around. So if you sub things in here and you got a negative answer, that would indicate attraction. If you sub things in here and you got a positive answer, that would indicate repulsion. But we don't want you to do that. Okay, it's one of those things that, as I mentioned to you, I've had little flutterings that I keep hearing about. Don't do it, don't do it. Make sure your students know they mustn't do it. And that tells me that although we don't penalize for it last exams, there's nothing to stop them from changing the rules and starting to penalize it from this exam. Okay, so please just be very, very cautious about putting charges in for either the value of the charge on an electron or any charge, unless you're doing the touching them together, or if you don't put a negative in, it's going to make your answer wrong. Okay, sorry, that was for Alex. If we leave the answer in decimal form, will we lose marks? That's actually a very valid question here. So going to this question, as it's been written here, sorry, I'm just trying to move my chat thing. Sorry, I'm going right to the bottom of my chat. Okay, so the question was, so I think everybody's managed to understand why I didn't put the negative in. Okay, I'm following on in the guidance that I've been given here. that charges or forces between charges are going to be attraction or repulsion, and you can look at the positive and negative and see which way around it goes. So please, I'm advising here not to put it in. At this point, to the best of my understanding, they do not penalize you for it in a matric exam, but it's one of those things where when they change the rules from it's kind of acceptable to know we're not giving the marks, they don't tell anyone until they've done it. You don't want to be caught in the middle of that, damn, I thought I had the marks thing. Okay, so at the end, you can check here. You're welcome to add in a direction just to be safe. I've never seen anybody ever get penalized for putting in a direction that they didn't need in any force. And then the question, sorry, that I was going back to was the one about decimals. Now, this particular one, if I left it in with decimals, and you're going to have to excuse my bad maths, it's been a long day here. 1, 2, 3, 1, 2, 3. I think I get 4, 3, 2. Let me just quickly check where my zeros go. 1, 2, 3, 4. Yes. Okay. The problem is if you left this like this, it would be fine. But if you decided that you were going to go on the 2 decimal places rule, and you then made it 0,00 newtons, you're not getting the marks. Okay, so you've got to be careful about what I say when I say you can leave it in decimal form. You can leave it as 0,000, but usually we find that we turn things into scientific notation when they're very small. Also, please be very careful. I know that students often miss the fact that there's even a scientific notation there, and their calculator says 4.32, and they're like, yeah, that's the answer. And they miss the 10 to the negative 4 because they didn't look down the side where it tells you the times 10 to the negative 4, okay, depending on what calculator you've got. So some people may struggle with that in terms of how to put it all together. All right. Okay, so I think I've managed to get through most of the questions on this. So the last thing that I just quickly need to cover, I think, on this, I'm only going to get to electric fields on Thursday. It's not my plan to get there today. It's technically a whole different question anyway. We've managed to do, by the way, everything for one entire exam question in this session. We may not have done all of the nuances of it, but we've done it, which is exciting. Okay, so, oh gosh, I can't remember what I was going to do. Someone's going to have to remind me what was in my head. Oh dear. Just gone completely blank. So, that's what I was going to do. Coulomb's law. Sorry, sometimes I need someone else up here to help me when I get a bit distracted. You are going to be asked to define Coulomb's law. Now, please, can I suggest, yeah, thank you, MZ's reminded me, you rock. With Coulomb's law, you need to know your definitions. I cannot tell you how important those definitions are. If you count up the number of definition marks in an exam paper, you can almost get you'll get half of your 30% pass mark just from definitions and multiple choices and guessing correctly when you've got 2 options. So there are a large number of marks if you learn your definitions, and there's some definitions that are asked very frequently. Coulomb's law is one of those, okay? So Coulomb's law says that I'm not going to do this word perfectly, I'm going to do it concept perfectly, that the electrostatic force of attraction or repulsion, I haven't yet hit a single mark, between 2 charged objects is directly proportional to the product. You've got to have the word product of the 2 charges and inversely proportional to the square of the distance. Now, many of you would say between their centers, and that's fine, but technically you can get away with just between them, because the between their centers is something that you learn from gravitation, where we've got giant planets with huge radii. Here we're dealing with little charges with tiny radii, and the radii usually don't make a difference. So when we mark this, sometimes they change the marking. It's either marking per concept or penalty marking, where they've got certain things and everything that you're missing loses you a mark. So I'd say that the important thing, you probably get away without electrostatic, but it's the force between two charged objects is directly proportional to the product of their charges, the two charges. There's a mark. And inversely proportional to the square of the distance between their centers is the second mark. So I recommend that you write the whole thing, because as soon as you write exactly what's being written and what you've been taught by your teachers on your formula sheets, everyone likes it because they can do nice ticks. Please be careful. The keywords that are often missed off here are product of the charges. People say it's directly proportional to the charges. Nope, directly proportional to the product of the charges. And you've also got to have the idea here that it is the square of the distance between their centers. Okay. Okay, I'm going to carry on with what I'm busy doing here. Everybody good with this so far? Okay, let's just quickly see. Where am I up to? Okay, cool. So what I thought we'd do from here onwards, and we've got about 10 minutes left. I did hope we'd get a little bit further today, but it's still kind of where we wanted to get to, is I want to just quickly share with everybody what's happening on Siavula. So I just quickly need to get into my Siavula account so that I don't manage to get myself locked out. Okay, so Siavula has been absolutely amazing, and they've put together for this class that I'm hoping to continue with. Where are we up to? Sorry, I've just lost everybody. There we go. Okay. So wrong share, sorry. Some days. Okay, they have been kind enough to put together a package for us. Now, Siavula's had this available to every single student in the country since the lockdown. What we've got that's rather special is that everybody that's coming to my classes gets put in my classroom, which means that I can monitor how much work you've done, what you've been doing with them, etc. So I'm going to ask you all right now, if you've got a computer, to please do me a favor and go to www.siavula.com. And when you get to, so I'm going to try and do it in another window, so www.siavula.com. Okay, hopefully you can still see what we're doing. It's already jumped me straight in. So you're going to have to, I think, log in. So there'll be an option. Yeah, it's not going to allow me to pretend I don't know where I'm going. Maybe it will. Let's try a totally new screen. Okay, so if we're going to siavula.com, is it already identified who I am? Okay, yeah, it hasn't. So what you do, oh, damn, it has already. Okay, so what you're going to have to do is you're going to have to set up an account. I strongly suggest you do this with the school that you're in, okay? But I do have a code for you all to join my class. I'm not quite certain exactly where the code goes, but if you go into Siavula, it should ask you for a code. I haven't had to come in through the back end, so I'm not quite certain. But the code, where did my code go? Sorry. Okay, you're going to enter this particular code. It's made up of 4 separate words, and they're science-related words. So if you put in direct, then a dash, fission, dash, genetic, dash, matter. So direct, fission, genetic, matter. And I'm going to add that just now in our WhatsApp group. It will allow you to join my classroom, which means that when you come in here, I actually have teacher dashboard, where are we? And I've got all of my things from school there, but also at the bottom, there's something that they put together for me called Lynne Special Projects. And you will join here, and it'll allow me to see what kind of things you've been doing during the day. So just in case you're not aware of it, Siavula has the most amazing online practice. And I'm going to be trying to get us working together on this, where they've got something called intelligent practice, which means that they change the questions, which means I can give you all the same question, except none of you will have the same values, none of you will have the same answers. So it could be something where there are 2 charges, but every one of you will have 2 different charges in a different distance between them, okay? And we can work from there. So if you choose to practice, this is a really nice thing. It's free until the end of end of this year, so you've got the whole of your matric year, you're not going to have to pay for it, is you're going to go in and you can choose to do science, grade 11 or grade 12. You may choose which section you want. It monitors how often you're active, what you're doing, how many questions you do. You can see I had some fun today and I got one of them right. And you can go through the syllabus of what you're doing here and particularly pick across the questions. Please just be aware it looks here like electrostatics is still under grade 11. So you may want to then go in here. I'm just going to have to quickly go back to the practice, to grade 11. Okay. Hopefully it'll find it here. There we go. So you can go into electrostatics and you can say, please, for this week, I only want you practicing Coulomb's law. I haven't yet done electric fields with you. So you jump into Coulomb's law, and then it would start asking you questions. So there'd be a question here which says two electrically charged objects are interacting. Both have the same negative charge. Here's the distance. Here's the force. What is the charge on each of the two objects? Now, I'm just quickly going to do this with you. We've got about 5 minutes left, but I think it's important because if I'm going to be doing this, I want you to be able to practice what you've learned now and check that you get it. So we've got two charged objects. They carry the same negative charge. Okay, the distance between them is that much and the force is that much. So if we're going here, we'd say F is equal to K, Q1, Q2 over R squared. I'm going to write all over the page, just excuse me here. So 6.91 times 10 to the negative 4 is equal to 9 times 10 to the 9. Then we're going to have Q1 and Q2. Now, I was told that they're the same, so I'm just going to make it Q and Q. Don't have to do anything fancy. I, in fact, go with Q squared rather than writing Q and Q. Over 3,84, my units are already in meters, so I can leave it there. All right, just quickly checking. I think there's a chat that I'm missing. Oh, that thing's in the way. There we go. Okay, so there we go. Someone's just said when you sign up, there's an option to enter an access code or a voucher where you enter the code and that's where you put it in. Sometimes there's a problem with being the teacher that you don't know how to go through the back end because you always come in through your end. But I know that they don't make it hard, so I did figure that somebody would work out how to do it. Okay, so what I'm going to do here is I'm going to get the Q is equal to 6,91 times 10 to the negative 4 multiplied by 3,84 divided by 9 times 10 to the 9. That's for Q squared, so it's going to be square rooted. I find that I work out my answer and only then do I square root it, otherwise it gets really messy. Okay, I'm hoping I'm going to get this right. I square root my answer, and I get an answer that Q, you're going to have to correct me if I've got this wrong because it's end of the day maths, is 5,429 times 10 to the negative 7. It says, enter your answer in scientific notation, use your calculator's psi mode, round your answer to two digits after the decimal commas, and any values for physical constants you need are listed here. Now, the reason they've done this is if people use slightly different constants, it doesn't work. Oh, I didn't want to do that. Okay, so that's all of their constants. Let's quickly see if I can go back. Yay. All right, so I got my answer here, and I'm hoping they're going to give it to me. So I'm going to say 5,42 times 10, and I'm hoping this is going to work to the negative 7. And then we hope. And it says check answers. And then it says, are you sure? Okay, take another look at your answer. It says, I may have typed it in wrong. How embarrassing. Okay. Can anyone tell me what I did wrong? Oh, I rounded it. Sorry, that should have been 429. So that should be 43. Let's just check if someone's got a better suggestion other than my bad rounding. Distance must not be squared. I don't think I squared the distance. I squared the Q. Sorry, just quickly checking one more time. Power I wrote is negative 7, but that's what it is. So I got 6.91. Sorry, I'm doubting myself. I'm not going to really fuss if I get it wrong, but it's to show you how the system works, not how I'm messing up at it. 9 times 10 to the 9. Ooh, I got it. Oh, I didn't square root it. 5,43 times 10 to the negative 7. Let's check. Okay, so I got told I got it completely wrong, and they wanted me to get, oh, what did I do wrong here? Oh, distance wasn't squared. Yeah, somebody did say that. Sorry. I was doing Q squared and I forgot to do my bottom square. I'm blaming it on a long day. Somebody did say that. Thank you. Apologies. But the point is, very bad when you've had a long day. I should have written out the formula and worked from it. If I'd done that, that would be squared and then my answer would be there. But the important thing I think from this, besides the fact that I've now shown you how not to do it, is that once you've got it wrong, okay, they give you a very motivational quote telling you that you haven't yet sucked. I don't know if you all noticed that. There was the, what's the lovely comment? Read it right at the top where it says, a winner is a dreamer who never gives up. Read the solution and try again. So you can all do that later. So there's my wrong answer, but it usually gives you a hint, as you'll see when you get something wrong, that you may want to try again. I did, and then I didn't have time. So then it's got a fully worked solution where it tells you exactly what the theory was. So they both got the same charge, okay? And then they look at the fact that you've got your equation, how you substitute things in, how you rearrange the equation. They rearrange it without putting the variables in. I prefer to put the variables in first. Then they calculate out a full final worked answer. You can see right till the end. Now, what's clever about the system is it says try the exercise again. Now, quite often when we do that at school, it means, oh, cool, we're just going to redo exactly what we've done. If I say try the exercise again, it's changed the distance and it's changed the force between the two charged objects. So I can now, on a completely fresh question, redo the question and check that I've really got the idea, not that I can just plug in what I did last time. Once you've got to the end of that, so I'm going to get this one completely wrong. Please, this is very deliberate. Okay, so I'm going to check my answer. It's going to tell me I got it wrong. Yeah, are we sure? So I'm going to do a final check. Okay, there's my next full worked solution. At the end, if you decide that you've really had it with this question, you can go on to the next exercise. And when we say the next exercise, it's now starting to look at things that are slightly more complicated. So their idea behind the intelligent practices is that it ramps up your questions as your mastery of a section improves. So the idea of mastery is by the time you get 100% for it, it tells you that you practiced enough. So it tells me how many questions I've done, how many people are practicing. And as I go through it, these stars, I assume, they used to do bars of mastery, but I assume that as you go through it, these stars will light up to show how much you progressed and how much you understand. All right, so please, can I suggest, I think everybody did get that code. I will send it again just now through the WhatsApp group, but I'll send through the codes that anybody who's interested can go on to Everything Science and Practice. If you do that, my suggestion is you do that from now until Thursday. When I see you on Thursday, we can then spend some time going over any particular concepts that are still an issue. Sometimes you're going to find that the issue comes in, as I mentioned, with how forces get brought into it. And unfortunately, we didn't have quite enough time today to go into forces as I'd have liked to. But what I plan to do with everybody then on Thursday is we'll start off probably with a relatively tricky one of Coulomb's law. And then after going through something that's a little bit tricky, we'll move on to examples where we do the electric fields. So at this point, if you want to be doing past papers, this is the next thing that I wanted to just make sure you understood you'd already got to. You actually already know enough from what we've done today to be able to go and attempt some of the question 7s. So any past exam paper, NSC Matric past paper, as I mentioned, you can get these from Parent 24. Question 7, we have covered most of the things. I haven't yet done electric fields, but electric fields should not be in question 7. They should only be in question 8. So this is a little bit of a naughty question. No, sorry, I lie. This question is a weird one. Normally they're two separate ones. No, Doppler came weirdly with this one. So June 2019 misbehaved itself just slightly. But if you go back further, the question 7 here, everything here is exactly what you should be able to do. And then we'll move on to electric fields. I haven't yet done electric fields with you today, but that will come on. So most of the stuff you should be able to do, usually electric fields get covers a little bit later. All right, so you're going to have a lie. You're not going to be able to do everything in question 7. You'll be able to do some of it. Okay, I'm just being proven wrong right now. Okay, Ladies and gentlemen, we come to the end of our time today. I know it's been a little bit of a rush. I think I've been a little bit anxious with having such a large group. I don't think I've ever taught a group even half as large as you guys. And I hope I didn't put you to sleep too much. I hope that you learned something. And then I hope that I'll see you again all in the next session. All right. Does anybody have any questions or comments just quickly before we get going? All right. I really do hope that many of you will still stay on next week and I'll still get to see you. I plan on managing to work the whole way through the curriculum, and hopefully as we get a little bit more used to working with each other, we can get into a situation where you're actually dealing with the grappling questions, which are the ones that are going to trip you up in an exam. But we've got to start from somewhere, and that place is usually a good beginning point. All right. It's been really nice seeing some of you. Can I quickly ask, just while I've got everybody here, because I haven't met many of you before, if you can all just quickly turn on your cameras so that I can quickly see the people that I'm teaching. Even those of you who may be asleep or in pajamas, I don't judge. You may have me in pajamas some days, except you won't. All right, so I'm going to quickly just run through. Sorry, they've got 3 screens of you. So I just quickly want to say hello. Wow. Gosh. Hello, Mark. Okay. Awesome. Anyway, thank you so much for joining me this evening. I'm hoping that we'll manage to get this going and keep the steam that we started with. And yeah, I'm committing to doing this till September, so I'm hoping that many of you will commit to being here. Please, this is regardless of what happens with when Matric schools go back and what happens. I think we've got enough upheavals that are going to take place over the next 3 months, whether schools are back or not, that it makes sense for us to have something as a bit of a backup, and some place also where you can ask questions. I know I'm probably going to regret at some point taking on nearly 200 other people's students, but I'd rather be here and be available to assist you than have you guys struggling on your own. All right. Okay. Have a lovely evening. Bye-bye, everybody. Haven't yet finished.
Can you please put the code on for that website?
My son's just pointed out I'm muted. Let me go back. Siavula, let me just quickly find where it is. Sorry, I've only just gotten back into using the Siavula platform, but Mark Horner was such an angel today that, yeah, his program is really, really good. We just haven't been using it for a while, which is bad. Where was I? Teacher dashboard. Okay. And access codes. Okay. So it's direct fission. Oh, wait, you can't share. I'm not sharing yet. Sorry. Share screen. There we go. Wow, 34 people have already signed on. Just need to make sure that we get 100 people, because Mark has very kindly paid for this platform, because I knew I was going to have more than 100 kids and I was getting panicked. So as long as I can get 100 people signed on, I can say, yay, see, I needed your codes. All right, have you got that there? Okay, let me just quickly jump back. Okay, so I'm going to stop sharing. Did you get that? You all good? Okay. You can all go now. I'm just waiting because I want to check in case anyone has any questions that I have to answer right at the end. You don't have to stay. It's just I stay till the end unless I'm in a hurry. Does anyone have any questions, or are you all just trying to get out? Got to push the end button. I'll make it easy. Bye-bye.